In this video, we're going to leave statistical tests behind and talk about another area of statistical inference, confidence intervals. With statistical tests, we are asking ourselves the question, could a difference between two samples have arisen by chance? But there are other statistical questions we might be interested in asking. Let us imagine that we have only a single sample and we calculate some value from that sample. Imagine, for example, that we take a sample of students and calculate their average height. Now, the average height of the small sample is unlikely to be exactly the average height of all students in the total population, but the total population average is what we are interested in. So we might ask a different statistical question. We might wonder, given that there is some random variation in our random sample, how close is our sample statistic to the population statistic? What we can essentially do is calculate a margin of error around the statistic, which in this case is the mean height. We call this margin of error a confidence interval. Imagine that we were to repeat the process of taking a sample from the total population of interest. Would the average height of each of these samples be exactly the same? Or would they be a little different to each other? Or would each sample's average height be vastly different to all the other samples? Pause the video here and think about this a little. Try to pick one of these three answers before you proceed. Well, the answer is that each sample would be a little different to all the others. But although they are each a little wrong, they would cluster around the true population mean. So if we were to take a lot of samples, we could look at their variation and get a pretty good idea of the interval in which the true population statistic probably lies. But often we can't take lots and lots of samples. Often we can only take one sample. How can we replicate the process of taking lots of samples from the total population when in reality we can only collect one sample? The answer is using something called resampling. You have already seen resampling in action, when we shuffled up the two samples using random permutations for the purposes of hypothesis testing. However, here we only have one sample, so we can't use permutations for calculating confidence intervals. Instead, we are going to use a different type of resampling called the bootstrap. The bootstrap is a very clever idea. What it essentially says is that our one sample is basically the same as the original population. Data that is rare in the total population will also be rare in the small sample that we've collected. So if we sample from our sample, we are essentially going to get the same result as if we sampled from the original population. And we can sample from our sample as many times as we like using a computer. We tell our computer, create 10,000 random bootstrap samples from our original sample, and calculate the average height for each one of those. And from that we can get an idea of the confidence interval, the range in which the true average height of the total population is likely to lie. This might seem a little strange, so I want to illustrate to you how the bootstrap works. Imagine that this is the original sample that we collected from our population. 5 people, one of them small, one of them tall, and 3 of them right in the middle. How do we create a new bootstrap sample? Well, we pick 5 new values from the original 5 values. There's an equal chance of picking any of them. So let's say that our first pick is the dark blue student. Now here's the important thing. Although we've picked this value, it's not removed from the values that we can sample from again. So when we pick a second pick for our bootstrap sample, we again pick from any of the original values in the sample, including the dark blue student. We could pick the dark blue student again. In fact, we could pick a sample that is entirely made up of the dark blue student, which would be very unlikely, but that's kind of the whole point. But anyway, we pick another value, and this time we pick the small yellow student. We repeat the process again, and we get the tall pink student. Then again, and now we get a duplicate value. We've picked the yellow student a second time. For our final value, we pick the green student. So what is the average height of our bootstrap sample? Well, we have one more short observation. So the average height is going to be a little shorter than the original sample's average height. It's possible that we could have picked the yellow student 5 times, which would have given us a very short average height. But again, that's statistically very unlikely. In fact, if we repeat the Bootstrap sampling procedure, we can generate a large number of samples, most of whose average heights will be pretty similar to the original sample. And in that way, we can get an idea of the variation in sample means that we would have got if we'd been able to sample repeatedly from the original population instead. If we generated 100 Bootstrap samples, we could say that the middle 95 lie between one average height and another. In fact, we could say that if we were to repeat the sample 100 times, then 95% of the time we would expect the sample mean to lie between these two extremes. This range is the confidence interval, and in the case where we consider the middle 95% of Bootstrap samples, it is the 95% confidence interval. We don't have to use a 95% confidence interval. We could look at the middle 90% of the samples and report the 90% confidence interval instead, for example. However, the 95% interval is often used. As with many statistical concepts such as p-values, it's important to be clear on what the confidence interval means. A confidence interval does not mean that the population value has a 95% chance of being within the confidence interval. It's actually kind of the opposite, a subtle but important distinction. A 95% confidence interval means that 95% of confidence intervals will contain the true population mean. In other words, if we go and gather data in many different experiments and calculate the confidence interval in each one of those experiments, then 95% of the confidence intervals will contain the true population mean. As I said, it's a subtle distinction, but an important one. When you calculate the confidence interval, you should report it using this plus-minus symbol that you see at the bottom of the slide. You should also specify the percentage of the confidence interval that you used. And to reiterate my earlier point on this slide, you should be careful with your interpretation of exactly what it means.